Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Welcome, agents, to Operation Data Vault Break-In. This is your mission briefing on the critical first phase of building a robust and highly secure Retrieval Augmented Generation system. RAG systems are the future of contextual AI, but they rely entirely on the quality and structure of the data assets we feed them. Today, we are focusing on infiltration. How do we prepare chaotic, unstructured knowledge so that our AI can access it with speed and precision? Think of this presentation not as a lecture, but as a technical blueprint for securing high-value assets and ensuring mission success. Our goal is to transform messy, real-world data, including countless PDFs, legacy database dumps, and sprawling web pages, into a highly structured, searchable format that ensures accurate, attributable, and trustworthy AI outputs. The entire success of our RAG system depends on the diligence of this preparation phase. Over the next few slides, we will break down the two critical phases. Phase 1, acquiring the schematics through precision filtering via metadata, and Phase 2, creating the semantic disguise using embeddings. We must adhere to the principles of absolute precision and uncompromised security, maintaining the context and access level of every single data point throughout the process. Let's begin the briefing and secure the data. Our target is formidable, unstructured knowledge. Our overarching objective is clear. We must build a retrieval augmented generation system that is not only fast and accurate, but fundamentally secure, compliant, and trustworthy. The RAG system is only as good as the input it receives. Right now, our primary asset, the vast institutional knowledge base we need to query, is locked away in what we can only describe as a chaotic vault of raw assets. Look at the diagram and observe the tangled mess. We are dealing with a complex mix of unstructured PDFs, dumps from relational databases, and sprawling, complex web page content. The defining characteristic here is the lack of inherent structure. This data was created for human consumption, not for the deterministic requirements of a machine learning system. If we try to feed this chaotic mess directly into an AI model and hope for the best, we are engaging in a simple brute force approach, and that approach is guaranteed to fail in any professional or high-stakes environment. We cannot rely on luck or simple keyword proximity. We need a systematic, surgical plan to impose order and structure on this chaos, ensuring that when the AI asks a question, it retrieves only the most relevant, contextually complete, and legally compliant piece of information. This necessity drives our entire preparation strategy, because without structure, we have no foundation for accuracy. To understand why a brute force approach fails, we must examine the limitations of pure semantic search, captured perfectly by the metaphor of the clueless librarian. Imagine you, the user, ask for a book on the history of medicine from your retrieval system. The system, relying purely on fuzzy semantic similarity, retrieves an obscure text on bloodletting from 1650. While bloodletting is, technically, a historical medical practice, this document is utterly useless, if not potentially misleading, in a modern context. The librarian was technically correct because the terms were related, but practically useless for solving the user's information need. This scenario illustrates the fundamental flaw of relying solely on similarity search. Semantic search is excellent at understanding conceptual similarity. It knows that indemnity and compensation are related concepts in a deep, conceptual way. However, without external structure, it lacks crucial, non-semantic context. It doesn't inherently understand non-textual elements like dates, source document names, security clearance levels, or mandatory relevance cutoffs. As a result, it will retrieve an answer, the one that is mathematically closest in the high-dimensional vector space, but critically, it will not necessarily retrieve the right answer that adheres to modern relevance or security standards. If we want precision and utility, we must supplement powerful conceptual search with deterministic, hard-line filtering capabilities. Our operation is divided into two highly specialized and interdependent phases: precision and disguise. This dual approach ensures both accuracy and speed in retrieval. Phase 1 focuses on precision filtering, which is executed using metadata. Metadata is essentially the schematics or the structured blueprint of our data asset. Before we can retrieve anything, we must capture critical structured information about the data chunk itself: its original source, its creation date, the responsible author, and what its specific access level is. This structured information is absolutely essential because it allows for deterministic, rule-based filtering. Think of metadata as our master keycard. It allows us to bypass specific locks based on exact criteria, for example, filtering out all documents older than January 1st, 2023, or restricting access to documents belonging only to the finance department. This provides the necessary foundation for security and exact accuracy. Phase 2 is the semantic disguise, powered by embeddings. Once we have the structure, we need to make the content searchable by concept, not just keyword. We translate the actual asset, the textual content, into a dense mathematical vector, a secret code the system can understand. This cryptographic layer enables the powerful function of semantic search, allowing the system to rapidly find similar concepts, not just exact keyword matches. The combination of precision filtering and conceptual search gives us a retrieval capability that is unmatched in both security and operational speed. Let's dive deeper into Phase 1, acquiring the schematics with metadata. Understanding the difference between probabilistic and deterministic queries is the cornerstone of effective RAG system design. Vector search, which forms the basis of our disguise phase, is inherently probabilistic. It finds things that are mathematically semantically similar. It's excellent for conceptual searches like find contracts about indemnity. It provides a highly relevant guess based on meaning. However, real-world business logic and regulatory requirements often demand deterministic results. They require things that are exact and absolute. For instance, a compliance officer needs to find contracts from 2024. Relying on a purely probabilistic vector search to correctly understand and accurately filter a date or a specific document ID is inherently unstable and a recipe for catastrophic failure. The vector model might interpret the concept of 2024 based on surrounding text, rather than treating it as a literal, hard constraint. This is precisely where metadata acts as our essential pre-filter. By tagging every piece of data chunk with structured attributes, like the exact year, the department, or the document status, we ensure that when a deterministic query is made, we can apply an exact, rule-based filter before the semantic search even begins. This rigorous process confines the search space to the exact parameters required by the mission, drastically improving reliability and reducing computational load. Once the raw, unstructured data is broken down into contextually coherent chunks, the unit of information we store and search, each piece is packaged into what we term the secure asset container. This container represents the atomic unit of our entire RAG system. It is a secure payload that holds both the asset itself, the raw content, and its manifest, the metadata. This structure is absolutely mandatory, as it ensures that the context and source traceability of the content are never lost during the retrieval process. The content might be a simple extracted sentence, such as, "The Q3 revenue was $1 million." But the manifest, the metadata, gives that sentence its meaning, its authority, and its security context. It specifies, for example, the date 2020-310-01 and the originating department, finance. For operational integrity and security, we require several key metadata fields to be extracted and attached. First, the source ID or URL, which establishes the asset's verifiable origin. Second, a timestamp, which is crucial for recency checks and version control, ensuring we never rely on outdated information. Third, the document hierarchy, which preserves the asset's location in the original vault, maintaining its relational context. And perhaps most critical for the entire operation, the access control list, which dictates precisely who is authorized to see and retrieve this specific asset. Our mission success is not just measured by accuracy, but fundamentally by security and regulatory compliance. This brings us to a mission-critical function, access control. Consider a high-stakes scenario. A junior employee asks the system, "What are the CEO's stock options?" If our system operates without rigorous safeguards, the catastrophic failure is predictable. The system, relying only on semantic proximity, might retrieve the answer from a confidential HR document it has indexed because the words CEO and stock options are semantically aligned. This results in a massive security breach. The essential solution lies in the access control list, or ACL, which is embedded within the metadata we attach to every chunk. We attach a list of authorized user groups, such as execs, legal team, or HR admins, to the metadata of every sensitive document. During the retrieval process, before any information is ever passed to the large language model or presented to the user, the system executes a mandatory deterministic check. It verifies the user's identity and credentials against the document's ACL. If the user's credentials do not match the required group, the document effectively does not exist for them in the search space. This implementation ensures zero-tolerance security. The bottom line here must be internalized by every operative. Metadata is not a secondary feature for enhanced search. It is the primary, non-negotiable security mechanism of the entire Retrieval Augmented Generation system. We now transition into Phase 2, creating the disguise with embeddings. We have structured the data with metadata, ensuring precision and security. Now we need the mechanism for conceptual search, which delivers speed and intellectual understanding. How do you explain abstract, complex concepts to a machine? You cannot rely on ambiguous human language. You must use mathematics, specifically coordinates in a high-dimensional space. An embedding model acts as a highly specialized translator. It takes our text chunks and maps them onto a theoretical high-dimensional mathematical map, essentially turning words into points. The key principle is proximity. Concepts with similar meanings or shared context are placed close together on this map, while unrelated concepts are pushed far apart. This transformation is our semantic disguise. It turns raw, complex text into dense, manageable mathematical vectors. This allows for incredibly powerful operations known as vector arithmetic. For instance, as famously demonstrated in the diagram, if you take the vector representing the concept of king, subtract the vector for man, and add the vector for woman, the resulting vector lands remarkably close to queen, demonstrating conceptual relationships. This capability is what enables lightning-fast semantic comparison, allowing the system to instantly find documents conceptually related to a query, even if they don't share any specific, surface-level keywords. Selecting the right embedding model is a pivotal decision that defines the cost, security, and performance profile of our mission. We have two primary categories of tools available for acquiring the disguise. First, we have the black box solutions, which are proprietary APIs offered by major providers like OpenAI, Cohere, or Google Vertex. The pros here are high performance and convenience. They offer state-of-the-art results, integration is seamless via a simple API call, and they require zero maintenance or infrastructure investment on our side. However, the cons carry significant operational risk. By using an external API, our raw, sensitive data must leave our network for processing, posing a potential security and compliance challenge, and there is an ongoing cost per token which can quickly escalate at high scale. The mission profile for the black box is best suited for rapid prototyping and general knowledge tasks where data sensitivity is minimal. Conversely, we have the self-hosted or open weights models, utilizing resources like BAAI's BGEM3 or the various mini-LM models. The benefits here are exceptional for high-security operations. The model runs entirely locally, offering air-gapped security, it's free from per token costs, and crucially, we maintain full control, allowing us to fine-tune it to our specific data domain. The main drawback is the infrastructure burden. It requires us to manage our own dedicated GPU compute infrastructure. This self-hosted option is therefore essential for high-security environments, massive-scale operations, or any domain-specific tasks requiring proprietary vocabulary understanding. For vaults containing highly specialized, technical, or unique knowledge, standard, off-the-shelf embedding tools are often inadequate. This necessitates an advanced technique, custom tooling, where we forge specialized embedding models. The fundamental problem is domain specificity. Standard embedding models are trained on the vast, general data of the public internet. They know Apple is both a common fruit and a major technology company. But what if you're secure? Internal Vault contains documents where the capitalized acronym, APPLE, stands for Automated Production Protocol for Linear Extrusion. If we use a standard model that lacks this internal knowledge, a search for Apple protocol is highly likely to retrieve documents about iPhones, corporate earnings, or perhaps even fruit packing processes, triggering a false alarm and direct mission failure. The model fails to understand your domain-specific vocabulary. When the standard tools don't fit the lock, we must forge our own custom key through fine-tuning. The solution is to fine-tune the existing embedding model. By training it specifically on our unique internal vocabulary, acronyms, and relational documents, we teach it the local dialect of our specialized knowledge vault, ensuring that it correctly understands and maps our specific technical terms, thereby eliminating ambiguity and enhancing accuracy. The process of fine-tuning, or forging these custom keys, relies on a powerful technique known as contrastive learning. This is how we mathematically retrain the model to understand our local dialect and make the critical distinctions necessary for accurate, domain-specific retrieval. The model is trained using a specific dataset composed of carefully constructed data points called triplets. Each triplet contains 3 components that define the relationship we are trying to teach. First, the anchor, which is the input query, for example, what is the Apple protocol? Second, the positive sample, which is the correct document that accurately answers the query, in our example, the confidential automated production protocol document. Third, the hard negative, which is the confusing noise that must be definitively ignored, such as the document titled, "The New iPhone from Apple Inc., which contains the keyword Apple but is contextually wrong. The training process is essentially a mathematical manipulation of the vector space. We apply a pull force, which mathematically forces the anchor's vector closer to the positive's vector, reinforcing the correct relationship. Simultaneously, we apply a much stronger push force, aggressively pushing the anchor away from the hard negative's vector. This training teaches the model the critical nuances and context-specific distinctions within our specific domain, guaranteeing that it chooses the correct, specific document over the semantically similar but irrelevant noise. As we encode our textual assets into embeddings, we must consciously optimize the payload, balancing vector resolution against retrieval speed and storage cost. This critical trade-off is known as dimensionality versus speed. An embedding's dimensionality is simply the size of its resulting mathematical vector. For instance, a vector of 3072 floating-point numbers versus a vector of 384 numbers. High dimensions, such as 3072, provide a high-resolution disguise. They capture the subtle nuances, intricate relationships, and complex details within the text, leading to the highest theoretical retrieval accuracy. However, this level of detail comes at a cost: slower search times and significantly higher RAM and storage requirements. Conversely, low dimensions, like 384, offer a lower resolution disguise. They capture the general gist or core concept of the content. The cost benefit is substantial. They allow for extremely fast search operations and are cheap to store, but the risk is potentially missing subtle, yet important, context. To navigate this dilemma, modern operations employ an advanced technique known as matryoshka embeddings. These specialized models allow us to generate the full high-dimension vector and then dynamically chop or truncate it to a smaller, low-dimension size without losing all coherence. This allows us to dynamically trade accuracy for speed on the fly, using the full vector for a critical, high-accuracy search and the truncated vector for faster, lower-stakes retrieval tasks, maximizing efficiency. Mission critical review complete. The assets are prepped and now certified ready for extraction. Let's quickly review the comprehensive data processing and preparation phase we just executed. We began by locating the raw assets, the unstructured data pulled from our chaotic vault. Step 2 involved breaking down this raw data into smaller, manageable, and contextually complete chunks, a process vital for retrieval relevance. Step 3 was critical for security and filtering. Each resulting chunk was meticulously tagged with a precise manifest, the metadata, which provides the necessary deterministic information for filtering, source attribution, and rigid access control. Finally, step 4 involved creating the intellectual disguise. Each chunk was transformed into a secret, dense mathematical code, the vector embedding, enabling lightning-fast semantic search based on conceptual meaning. The successful result of this meticulous preparation is that we now have a collection of perfectly prepared assets, which we affectionately refer to as floating-point gold bars. Each bar is rigorously tagged with metadata and encoded as a vector. They are now ready for secure storage and, most importantly, rapid retrieval by our Retrieval Augmented Generation system, ensuring high accuracy, speed, and uncompromised security. Our assets are now perfectly prepared, structured, and vectorized. However, they are still operationally worthless if we cannot store them securely and retrieve them instantly, in milliseconds, when the AI demands them. This brings us to the next, crucial phase of the operation, the getaway vehicle. The getaway vehicle for our high-value data is the vector database. This specialized database is fundamentally engineered not for storing traditional relational tables, but specifically for storing and indexing the dense, high-dimensional mathematical vectors we just created. It is the core engine that transforms our preparation work into real-time, functional query capabilities. In the next briefing, we will explore the internal mechanisms of this vehicle in detail. Specifically, we will dive into the specialized storage and indexing algorithms, such as hierarchical navigable small worlds, or HNSW. These sophisticated algorithms are the secret sauce that allows the vector database to efficiently navigate through millions or even billions of vector dimensions and identify the closest matches to a user's query at the speed of thought. This transition from static, prepared data to dynamic, instantly searchable knowledge is the final operational step before we launch the Retrieval Augmented Generation system itself. Get ready to load the payload. The vector database awaits the final stage of the mission.